Hello and welcome back to Calculus 2, section 7.7, numerical integration. So far we explored number of integration techniques, 7 or 8, whatever it is. Basic integration, use substitution, backwards substitution, by parts, trigonometric integrals, trigonometric substitution, the partial fraction decomposition, and all of those techniques are called analytic techniques because you are able to integrate and then find the exact answer for the area under the curve if you are given the definite integral. Now, certain functions cannot be integrated. Now, we know that there is correspondence that if you find the derivative of, let's say, x squared, you are going to get 2x, which means that the integral of 2x dx is x squared, and then we put plus c just in case, right? We also know that we can find a function f of x dx that actually doesn't have an integral, which means that this will not be an answer if you differentiate. There is no function whose derivative will give us this, which we need to integrate to get the answer. So it's a little bit convoluted, but the bottom line is certain functions cannot be integrated. Every function can be differentiated. Maybe it's not differentiable at one or number of points, but we can technically differentiate anything, but we can't integrate certain things. So because of that, because of the fact, and I'll write it here in red, some functions cannot be integrated. Because of this, we defer to numerical methods to find the best possible approximation for the answer. We obviously develop these methods and practice on the functions that are known and we can integrate and check. And then we employ those methods with functions that are somewhat similar shape and so on, and there are other criteria as well. So I'm going to first work on the problem that you are supposed to know now from your Calculus 1. I'm going to use left-hand sums to calculate the area under the curve, and then I'm going to do that problem using analytic methods, and we are going to see that those two are close. And then we are going to develop 3 different methods, mid, trapezoid, and Simpson rules, and apply all of those rules to the same problem to see first how they work, and then also to see that they're all the same, close with their answers. So this problem is in Calc 1, Chapter 5. I want to approximate area under f of x equals, say, square root of x on interval 1 to, I don't know, 9. It's going to be too much writing. It's going to be way too much writing. 1 to 5. 1 to 5. Using left hand approximation. So how this works? We draw our square root function and then say 1, 2, 3, 4, 5. And then I create from each one, I create the left rectangle. We use n equals to 4 rectangles, because in that case this dx, which is known as delta x, is 1. So this is our f of x equals square root of x. So what I have is 4 rectangles. So the area is approximated by square root of 1 times 1. That's the height of the first rectangle is 1, because square root of 1 is 1. And then dx is 1. So that's area of the first rectangle, plus the next rectangle, rectangle number 2, is the square root of 2 times delta x, which is 1. Actually, you know what? Let me write the formula first. So it's going to be f of 1 times delta x plus f of 2 times delta x plus f of 3 times delta x plus f of 4 times delta x. And that is, function is square root of x. So f of 1, we can actually see that we can kick out delta x, right? We can factor out delta x. I'm going to write out all of the steps the first time, if you want to do them. And now delta x is 1, square root of 1 plus square root of 2 plus square root of 3 plus square root of 4. Note that there is no square root of 5. And the reason is value 5 doesn't have a rectangle to its right, because that needs to be the left point. Number 5 is not a left point of anything. The other ones are. If I was to do the right sums, then 5 would be included, but 1 would be excluded. Do we all see that? Good. So now we just compute this. We have 1 times this is just this. So it's 1 plus 1.4 plus 1.7 plus 2, which is 5.1. So area is approximately 5.1. Now I can do this integral. Is me bragging, right? I can do this integral exact and calculate exact area and see how well our 5.1 holds. So that's integral from 1 to 5 of square root of x dx, which is x to the 3 halves divided by 3 halves from 1 to 5. So this is going to be 2/3, 5 to the 3 halves, minus 1. Now this is exact answer, and you can go use the calculator to figure out the value. So I'm going to, where's my debit time? There we go. So 5 raised to the 1.5 minus 1 times 2 divided by 3, and I get 6.8. All right. Our method was not that great, but you have to consider how much error there is, right? So all of this stuff that it's in red over here, that's all error. And that's a lot of it. This method is not particularly good method. It works. I didn't say it's good. I just said it works. So we got something that remotely looks good. Can we do better? And this is where Calc2 begins. The answer is yes. We can learn about midpoint rule. So for midpoint rule, I will draw this larger now. This is a single delta x rectangle, because I want to explain how this works. And now what I'm going to do is I'm going to go in the middle and draw this vertical line that will hit the function and set my my rectangle to go through that line. Observe how well this balances error on the other side. I have errors on both sides of the line, but on one side I overshoot, on the other I undershoot, right? They don't cancel each other exactly, but they cancel a lot, actually. So if you go to the previous problem, there was no balancing out. It was just straight up piled up error. And the way to eliminate that error is to introduce more rectangles. More rectangles would make error areas smaller. And if you use infinitely many rectangles, you are doing the Riemann sums, which means you are doing the integral at that point. But now with the midpoint rule, we don't have to really do more rectangles, because you see how on one side you overshoot, on the other one you undershoot for the area, and they roughly cancel out. Not completely, but roughly. So now what is the deal over here? I'm going to have this point over here to be f of x, let's say n, xn, and the point on the other side is xn plus 1, which is the next point. That means that the point in the middle is the average of these 2 points. That's how you find the location of the middle point. And then this point here on top will have the functional value f at xn plus 1 over 2. So that would be the y value, which is the height of the rectangle. So what is the formula then? The formula is, and I use m instead of area. So mn, n stands for the number of rectangles, is delta x, and then you have times f of x0 plus x1 over 2 plus f of x1 plus x2 over 2 plus f of x2 plus x3 over 2 plus all the way to the last term, xn plus 1, xn minus 1, xn over 2. This is actually the formula for the midpoint. This is the one that you need to remember. As soon as you finish your partition of the x-axis, you will have points x0, x1, x2, x3, and so on, and you will just plug them in the formula. So let's do the same problem, the square root of x, using midpoint rule and see if it does better. So I have f of x is equal to root x, and I also have interval 1 to 5. So I draw square root function. One, two, three, four, 5. But our rectangles would go off of the middle. Now that happens at this point here, 1 plus 2 over 2. Next one is 2 plus 3 over 2. Next one is 3 plus 4 over 2. And the last one is 4 plus 5 over 2. That is this business, guys. What are you going to plug in into your formula? Stream died again? Yeah, the network issues. So the values over here are x0, x1, x2, x3, and x4. Can I squeeze that in here somehow? So this is your x0, x1, and then x1, x2, x3, and x. It's extremely small. The original values on the x-axis, yeah. So the points on the x-axis are your x0, x1, x2, x3, and x4. I should have made this picture. No, because the interval starts at 1. That's why I don't have it. All right, so let's take a look. So area is approximated by M4 in this case. Midpoint rule with 4 rectangles. I have delta x. Oh, we also see that delta x is 1, right? If you don't remember the formula from your Calculus 1, delta x is b minus a over n. A and b are interval, so that's 5 minus 1. And n is the number of rectangles, which is 4. So delta x is 1. I'm writing out the averages here for functions. And now all we need to do is to plug the numbers in. So this is equal to delta x is 1. And then I have the first average, which is square root of 1 plus 2 over 2. Plus the next average, 2 plus 3 over 2. Plus the next average, 3 plus 4 over 2. Plus the next average, 4 plus 5 over 2. We don't need this 1 in front, and we simplify fractions. So this turns out to be the square root of 3/2 plus the square root of 5/2 plus the square root of 7/2 and then plus the square root of, I can't read this, 4 plus 5, 9/2. So all we need to do is to add these values, and we're hopefully going to get something good. How much? 6.8. Wow. On the first decimal, this is exact.
What happens if the distance between each of, I know with the Calculus2 was very much if we also talked about the difference between these bases. If it's like 1 to 3, then 3 to 4, how would we?
We are going to deal with that when I finish all three, because we have extra example that is not 1. I'm just doing this for simplicity so we can efficiently get through this. So that's your midpoint, guys. Midpoint is going to take the averages on the endpoints of each of the rectangles, and then you are going to use that. Now, all of these methods, left-hand rule, right-hand rule, and mid rule, are all approximating with the rectangle where the line is horizontal, so you actually have the rectangle, and horizontal lines are constant lines, so this is also known as the constant approximation. The next one that we are going to do is called trapezoid rule, and the trapezoid rule has linear approximation for the first time. Simpsons rule is going to be quadratic approximation, and then if you continue studying mathematics, graduate level will teach you cubic splines and some other cool methods. So now we are going into trapezoid rule. So for trapezoid rule, I have, again, some function, f of x, and I have this wide. This is from xn minus 1 to xn. So now what trapezoid rule is going to do is going to pick up the corner points and connect them with a straight line. So you see there is some error there. No balancing of any kind in this case. And what you should realize is that the height of this line here is f of xn, and the height of this line here is f of xn plus 1. So if you take this trapezoid and draw this trapezoid on a side like this, you would have this to be your delta x, you would have this to be your f of xn, and you would have this to be f of xn minus 1. Now, if this xn minus 1 is intimidating, that just means the previous number. That's all it is. So let's apply this to our square root problem. So f of x is equal to square root of x on interval 1 to 5 again. N is equal to 4. And we draw the function. So this is 1, 2, 3, 4, 5. So this is your x0, also known as 1. This is your x1, also known as 2. x2, which is 3. x4, No, x3, which is 4. And x4, which is number 5. Your job is to draw this sorry, I did mid-rule. So you pick the points and draw straight line segments. So the area that we are going to get is close, but it's not going to be the same. It's not going to be exact. So let's see. The trapezoid rule formula is Tn is equal to delta x times, and now I have f of x0 plus 2f of x1 plus 2f of x2 plus f of x3 2f of x3 plus 2f of x4, and then finally plus single f of x5. These formulas look crazy, but they're not actually. Oh, I forgot over 2 over here. Sorry. Put the over 2 for dx. Otherwise, it's going to be wrong, whatever you do. Look, guys. To find this line, I have these 2 points. So f of x0 and f of x1. I forgot to tell you the area. Probably you don't remember. The area of the trapezoid is the midpoint, not the midpoint, the average of the sides times the height. So average of the sides, in this case, is f of xn minus 1 plus f of xn divided by 2. So this would be the average. And then I multiply that by delta x to get the area. So this is where these 2's come from. So what I have is, these are all the averages, and over here you have delta x over 2. So time delta x for the area, and over 2 is from the formula from trapezoid, where you take the difference. Yes?
What happens to that 2f of x5?
Oh, well, I'll address that. Okay. So if you look at the pattern, only first and the last point don't have 2 in front of them, and every single one, the other one has y. Look, this one is used only once in calculation for the first area of the first trapezoid. Second trapezoid is using x1 again. The third trapezoid is using x2 again. So technically, x0 and x1 are used for the first area, and then x1 is used with x2 for the second area, so I use this twice. That's why. And the ones on the endpoints I'll only use once, because there's no trapezoid on the other side to use this one more time. Yes? x0, x1, x2, x3. Oh, yeah, you're right. That's it. There's no x5. That's what you meant. I thought you were asking the same question as Kevin. Okay. Yeah, there's no x. Sorry, there's no x5. It's x4. So plus single x4, and then we're done. apparently after this formula we're done. So let's approximate our area using trapezoid with 4 rectangles. Delta x is still 1, so we have 1/2. And then I have a square root of 1 plus 2 square root of 2 plus 2 square root of 3 plus 2 square root of 4 plus single square root of 5. And all we need is to calculate this. And we'll have, I guess, Maha, our secretary here, or the sponsor for exact answers. How about that? Is that a better title? 6.76. We know it's 6.8 that we got on the exact calculation, right? So it was rounded 6.8. This is pretty damn close, right? The midpoint did better, but then the midpoint, guys, that's your trade-off. Midpoint has a lot of calculations, right? You have to find every individual average and then multiply by delta x, then you add them all together. Over here, you just plug into one formula, grind through it very quickly. The result is not as awesome as the midpoint, but it's pretty damn good, so it's okay to use this. I mean, otherwise it wouldn't be in math book. It would be in the book of conspiracies. The last method is the Simpsons method, which is quadratic approximation, which means now we have to use 3 points at a time. Now, this one has the restriction, n must be even. That's the restriction. Make sure you know this. A troll question on the test is use the Simpson rule with n equals to 5. It's a troll question. Because all you need to do is to answer. You cannot use Simpson rule on 5 rectangles. And that is because the pattern would not work. You know how there was a pattern to the previous formulas? The mid rule had function of the average plus the function of the average plus the function of the average. So it was a pattern times delta x. Trapezoid rule has delta x over 2, and then the coefficients for x0, x1, x2, and so on are 1, 2, 2, 2, 2, 2, 2, 2, 2, 1, right? So you can have 100 rectangles. The 98 rectangles, the 98 numbers in the middle will have 2 prefix, and the ones on the end will have 1. So there is similar derivation to this, to the trapezoid rule. You have the parabola now, right? And the parabola needs 3 points. Now 3 points is the span of 2 regions, and that's why you have even number of rectangles. It ensures that you can fit all of the points. So this one is going to take xn minus 2, xn minus 1, and xn. So those are the arbitrary somewhere in the middle. And what it does is it takes these 3 points here and fits a quadratic curve through those, which is the reason why this is called the quadratic approximation. So that's the second order. So what's the formula for Simpson's rule? The formula for Simpson's rule, Sn, is delta x over 3 times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus f of x0. So this formula is geared also towards our problem. But you remember how I said the trapezoid rule? The pattern is 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1. And you get to say this 2, 2, 2, 2, 2 many times because you might have 8 or 9 of these rectangles, right? Partitions. Now observe the pattern here. It's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 1 at the end. So it has to start 1, 4, 2, has to end 2, 4, 1. Now, this is the pattern for our problem. So this formula is tailored to our problem. But you might have to insert more pairs that will be 4, 2, 4, 2 in the expression. So the first and the last are single, then the second one in are all 4s, and then the 2, and then you can insert here another 4, 2, 4, 2, 4, 2 for additional 6 or 8 or 10 or 12 partitions. Yes?
Is that last step supposed to have 0?
Yeah.
No, it's not 0. What do you mean 0? It's a 4. No, it's just the tablet's passed. Here, look, 4.
There it is. Now I can see it.
Perfect. The calculation is just plug the numbers in. I said middle school, so it is middle school. We have that the area is approximately calculated with a S4, which means Simpsons, with the 4 rectangles, 4 regions. And we have 1/3, 1 time f of 1, plus 4 time f of 2, plus 2 time f of 3, plus 4 times f of 4, plus f of 5. All I did is I plugged the values 1, 2, 3, 4, 5 into the formula, and now we write everything else. So it's going to be 1/3 times, this is a square root of 1, plus 4 square root of 2, plus 2 square root of 3, plus 4 square root of 4, plus square root of 5. What happened? 4 square root of 2. It is 4 square root of 2. Of course I'm right. Except when you catch me every time when I'm wrong. Arrogance, right? Math world. Now, how much is this thing? 6.79. You are memorizing 3 formulas and you are plugging into those formulas the numbers and the functions, and then you work out the algebra. So I want to work out a problem that it's not, you know, this with a different partition and so on.
May I ask you to find the interval between points? Is the same thing for this? You said the f of parentheses n minus 1 plus by f n divided by 2.
I never talked about this.
Like this.
That was the
Trapezoid. And so there's something different from this.
Oh yeah, you use the 3 points. So the 3 points that you get on the line are all x0, f of x0, x1, f of x1, and x2, f of x2. And then you have 3 points, and then you set up your the matrix to find the values.
Where do I find delta x?
That's delta x is always b minus a over
Okay.
x. That's always.
So
The proof for that one is not easy at all. You use the matrix, so you have to find All right, let's figure out something that cannot be integrated in Calculus 1 or Calculus 2. Calculus 3 and others will take care of this. So here's the integral that you cannot integrate in Calculus 1 or Calculus 2. Integral of e to the x squared dx. And let's say you want to do this integral on 2 to 5, let's say. 2 to 5. Use all three methods on n equals to 6. So I want 6 rectangles. Do the midpoint first. You have the formula. This is your function, clearly, right? That's the function that you will be using. And it's just annoying, right? So get your calculators, your cell phones, whatever you have. And start practicing. So I'll give you 2 minutes for the first, 3 minutes for the second, and 4 minutes for the last. So that's altogether compounding at 9 minutes. Yeah, you can math. Guys, draw the picture to see the intervals. It's not 2, 3, 4. N equals 6 on this is just terrible numbers. The numbers are awful over here. Right? 2 to 5. Yeah.
was 35. It's 356. A lot of numbers. What's yours? 1, 4, 6, 6.
I got 3, 1, 6, 7, 3, 4, 1, 5.
What's that?
You gave us square root and some of the words. I said 2, 3, 6, 8, 7, 13, 13, 30. I would take that 1, 2, 3, 4, 5. Yeah, I kind of realized that. But is there a quick question? How do you do the integration of e to the x squared following curve?
It can't be done. That's why we're doing this. Right. Let's take a look. So, as I said before, we need to draw the interval so that we know what is actually happening. I'm going to draw the interval and see that I'm starting at 2, and then I need to have 6 divisions. So 1, 2, 3, 4, 5, 6, and then there has to be 5 at the end. So now you have to split this. Now the best way to do this is to actually use the formula for dx, which is b minus a over n. You have everything, 5 minus 2 over 6, so you get 3 over 6, which is 1/2. So you see that each one of these intervals is a half, which means that these numbers are 2.5, 3, 3.5, 4, and 4.5. You might be able to figure these things out in another way, but the best and the safest way to go is to do the dx. Because, I mean, I gave you the interval which was 3 with 6 rectangles, so it worked to be half. But they could be off on having 5 rectangles. You can't do Simpsons, but you can do the other 2. 5 rectangles on this interval of 3, right? Then all of these values will be fractions. So you have to be careful of the partitioning. It's still middle school math, but gotta get used to it. So what do I have for the midpoint? Midpoint, I have, so that's mid 6 rectangles. It's going to be delta x, which is 1/2, times the function computed at 2 plus 2.5 over 2, plus function computed at 2.5 plus 3 over 2, plus dot, 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 all of those, and the last one is function computed at 4.5 plus 5 over 2. Yeah, we're going to solve it. It's just too much writing. So now, the next one is 1/2. We have to plug in the function. So each one of these computes to a number. 2 plus 5 is 4.5. Half of that is 2.25. So we have e to the 2.25 squared plus e to the 2.75 squared plus e to the 3.25 squared plus e 3.75 squared plus e 4.25 squared plus e 4.75 squared. So we are looking for the midpoint for each one of these. Midpoint is calculated when you average the 2 endpoints. So the midpoint here for the first rectangle is the average of these 2 first points. So that's the average. And we have to compute the function value at that value. So this is 2 plus this 4.5 divided by 2 is 2.25. And we have 6 of them. So midpoint here, midpoint here, midpoint, 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 right? So you have 6 of those. And you pick up the pattern, 225, 275, 325, 375, 425, 475. Those are all the middles. And then we are plugging those for x. Now, our function was e to the x squared. It could have been anything else. You would have to plug in those numbers for x. It doesn't matter how complicated or how simple it is. We had square root of x earlier, so we plugged in just root number. It was, now you have e to the x squared. Now, the rest is just annoying, right, calculations. You square these numbers, and then e, and then add them, and then half. So that's now calculator work. So to square each one of these, and then take the half at the end. So 1/2 e to the 2.25 squared. We'll have Maha in charge. How much? 5.0625. Plus e to the
7.5625.
Thank you very much. Plus e to the
10.5625.
Plus e
14.0625.
Plus e to the
18.0625.
0.625 plus
22.5625.
5.625. The last one, 5.625.
Yes.
So now these are all the numbers squared. Now it goes e to each one of these, then add, divide by 2, So what's just the final answer here now?
318,146,6782.
Who picked this problem? Is that what Wolfram says?
Wolfram says this is the imaginary number. Wolfram says this is 3.18147 times 10 to the 9. Yeah.
Yep. 10 to the 9. Nice. 3.18 times 10 to the 9. Yeah, perfect. All right, so this was the midpoint. So what we did for the midpoint again is every middle. We get to recycle now some of this work. Trapezoid for the same 6 is going to be delta x, which is 1/2, divided by 2. And then we have function at 2 plus 2 functions at 2.5 plus 2 function at 3 plus 2 function at 3.5 plus 2 function at 4 plus 2 function at 4.5 plus a single function at 5. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. Good. But it's 6, right? Because this is endpoints on each, right? It's 6 pluses. Think about that. Because this one and this one both sit at the end. So this is number 1. And then this one and this one sit on the end. That's where number 2 is. So that's why you have that many. So this is 1/4 e to the 2 squared plus e to the 2.5 squared plus e to the 3 squared plus e to the 3.5 squared plus e to the 4 squared plus e to the 4.5 squared plus e to the 5 squared. E to the 4th plus 6 e to the 6.25 plus e to the 9 plus e to the 12.25.
All those U's have 2's in front of them? All the ones crammed in the middle?
Yeah, they have. Oh yeah, as you can see, they all have it. Plus 2e to the 16 plus 2e, see, they're all 2's. 2e to the 20.25 plus e single e to 25. Maha? 10 to the 10th?
Wait, how are you able to determine in scientific notation how to do that?
Well, the calculator gave the scientific notation, which is just move the decimal point 10 spots. But I don't like this result. It's a lot of error. Oh, the trapezoid rule. Trapezoid rule has only positive error. Okay. Is that no, it's your job. We will all blame on you if this is wrong. It's called taking responsibility. Oh yeah, you're already in corporate, right? So that's why. Take responsibility and risk taking and throw it out the window. It's always someone else's fault, and it's divided by 4.
Yeah.
Is your calculator okay? It's too far away. You got the same thing? Oh, I believe you then. No, because it was confirmed by. We go back 6 months. It will make her feel better. Simpson. 1/2 divided by 3. F of 2 plus 4f of 2.5 plus 2f of 3 plus 4f of 3.5 plus 2f of 4 plus 4f of 4.5 plus a single f at 5. So Simpson's rule, again, you use all of the points and you alternate the pattern 1, 4, 2, 4, 2, 4, 2, 4, 1. Divide delta x by 3. You will recycle the same values like here, except the coefficients are now 4. So this thing is 1/6. And then you have the same, and then the 4, and then a 2, and then a 4, and then a 2, and then a 4, and then a 1. So you technically copy this row, put 1/6, and this is a 4, and this is a 4, and this is a 4. That's it.
It would be like 1, 4, 2, 4, 2, 4, 1.
Yeah. So you are memorizing the formulas, and the rest is just. So your homework, if this is overwhelming now, I'm telling you this is the middle school level stuff. If it's overwhelming right now, it's because just so much writing. As soon as you figure out that this is, you have a formula, you just plug in. The trickiest part is to figure out what delta x is using the formula and having the right partition. The rest, if you don't know formula, obviously you can do it. And obviously if you make calculation errors along the way. But the work for this is identical to, I mean, the trapezoid and the Simpsons are pretty much identical. So we have e to the 4th plus 4e625 plus 2e9 plus 4e1225 plus 2e16 plus 4e2025 plus single e to 25. For the grand total of You got that too?
I got that too.
Off of this line?
That exact line.
So Wolfram says what? And you had the same answer, Wolfram and the calculator. Now you typed something wrong. 8 point.
Oh no, I got the same answer as her.
Oh, did you use the Simpsons rule there, or? I did it. The only thing I haven't done is I haven't plugged it in the calculator. But oh, to plug in the calculator? Yeah, what else are we gonna do?
Make sure Midpoint's right.
Oh, mine's definitely gonna be wrong. Because I gotta dust off this thing first, check if there is a battery on this. Let's see. There you go. It works. You know. You know what's the sad part? Like this most annoying thing, this is more important than anything else you learn in this book, technically. This is how Mathematica and all these do definite integrals. They don't know to plug upper limit minus the lower. No. 10,000 rectangles, 100,000 rectangles. That's how it's done. So you understand this section, you can integrate any definite integral. Yeah, you understand that I'm doing this to be happy. I completely trust those guys. Now 1.242. And all right, so that's it. Now I just want to show. I'm going to erase this. I want to show one of the, let's say, annoying partitions. Say n equals 5 on interval 1 to 7. That will be annoying partition. Draw, all right? You're going to have one, two, three, four, 5. So here they are. 5 partitions. We know that the first one has to be 1 and the last one has to be 7. Question are, what are the other numbers here? Well, each one of these is delta x. That should be common sense by now. So delta x is 7 minus 1 over 5, which is 6/5. So the first one is, so each one of these is 6/5. So 1 plus 6/5 is 1 plus 5 plus 1, so that's going to be 11/5. Plus 6/5 is 17/5. Plus 6/5 is 23/5. Plus 6/5 is 29/5. And then plus 6 is 35. 35 divided by 5 is 7. That's how you check. So I'll do this one more time. Over here, you start with a 1 plus 6/5 is 11/5. Now all the common denominators are already 5, so common denominator is 5, so 11 plus 6 is 17, 17 plus 6 is 23, 23 plus 6 is 29. Checkpoint, 29 plus 6 is 35. 35 divided by 5 is 7. It has to land right there because you did delta x formula. So that's how the partitioning works. You can have any combination under the sun, and these will most likely work out to be fractions, unless I fix it so the integral is 2 to 6 with 4 rectangles. Well, obviously 2, 3, 4, 5, 6, right? But as you can see, that doesn't work. Further, n is odd, can't do Simpsons in this case. Look at the pattern. 1, 4, 2, 4, 2. I have to finish with 4, 1. 4, and I don't have enough for 1. 4, 1, 2, 4, 2, 4. No, sorry. 1, 4, 2, 4. I can't do 1 here because I have the next one, right? So either way, you can get with the odd, can work out odd and for Simpson. But you have trapezoid, you have midpoint. And if you haven't figured out by now, the midpoint tends to be the best for most cases, right? Because of that cancellation on both sides. One problem on the exam, because it's really annoying to compute this stuff, might have anywhere from 4 to 6 rectangles on it. Generally, depending on how the rest of the test is, it might be pick your method, or it might be you must do ABC. But definitely only one problem on this, because this is, as I said, something that you need to know if you are to program a machine to do this for you for some more complicated integral you ran into as you did modeling. And that's it. We'll say bye to the people watching. Thousands of people. All three. Bye.